So the general problem setting in this case is that we search for clusters in subspaces of the original feature space, and these subspaces are in the general form arbitrarily oriented. Yeah, so we are in this specific problem here, we search for clusters that are similar in an arbitrarily oriented subspace. And the special case, of course, is this one here, that the subspace is axis parallel. But in general, it is usually the case that we are that we search for arbitrarily oriented subspaces. Yeah. So that is the general problem setting, and all of a sudden we have two challenges now to solve. Well, first of all, this is the second one. We have the original problem that we have to find the correct clusters in the relevant subspaces, but we want to find the correct clusters. And the second challenge now is that we also need to find the correct subspace of each cluster. Yeah. And when looking at the search spaces of those things here, well, the search space for the clustering is or depends on the clustering algorithm. Yeah. So it's just, yeah, that's depending on the clustering algorithm. The search space for the correct subspace of each cluster is virtually infinite, because all possible arbitrary oriented subspaces of a feature space, that is anything, that is infinite, at least virtually infinite. Yeah. So yeah, this red line here may be, yeah, just rotated by 360 degrees, and any of these rotations is one possible relevant subspace. So there is an infinite number, or at least virtually infinite number, of those subspaces. Well, that's not a good story, and the story will get even worse, because both challenges actually depend on each other. In order to determine the correct subspace of a cluster, well, we need to know at least some cluster members. Well, if we know some cluster members, then we can just apply PCA or stuff like that, and we are good. But it's unsupervised, so we typically do not know some cluster members. On the other hand, in order to determine the correct cluster memberships, we need to know the subspaces of the clusters, because, well, in this case, if I don't know the relevant subspace, those guys here are not clustered at all. So in order to find this cluster, I need to know the subspace. In order to know the subspace, I need to find the cluster. So there is a kind of vicious circle or circular dependency between these two challenges. Yeah? And this is, well, not so easy, especially in practice. Yeah. So this is just a slide with some philosophical notes, actually. So here just, yeah, even if we found the relevant subspace, we still might have a hard time to find the correct clusters. So take this one here. So this is the correct subspace to identify the green cluster. But still, if we project that on this perpendicular subspace here, on the relevant subspace for the green one, we will still have a very hard time to find the green cluster, or at least distinguish the green cluster from the rest here. Yeah. So clusters here and noise are not really separable in the correct subspace. The same holds true for the red one, which is somewhere here, and maybe even for the green one, which is maybe here. Yeah, somewhere here. So obviously, the whole thing is a little bit more complex than weapons. So we don't have the correct weapons to shoot at somehow. So yeah, typically in that case we would need a new cluster model. Yeah. So and now this is really a kind of abstract view of the whole thing. So a cluster model is typically, I mean, what is clustering? Well, clustering is we want to find groups of similar objects, and a cluster model somehow defines what is similar, when are objects similar, and when do objects form a group of similar objects. Yeah, so defining a different concept of grouping and similarity might help here, but still it's very hard to come up with a very good or suitable cluster model to find these three clusters here and the surrounding noise. The question would be, if we want to come up with something like that, is what is the concept of similarity that all members of a cluster share? And in this example, it is hard to really come up with something like that. So is it something that they should be on a common correlation? So meaning they are on a common line, like this one here. Well, at least for the even for the yellow ones, that doesn't pay off. So again, it's hard because we need a concept of similarity that all members of the cluster share, but all the other non-cluster members do not share. And this is hard here because this is a really nasty example. But that is the original problem. We would need to come up with a concept of similarity or a cluster model that accommodates that, which is in that case, as I said, a little bit hard. Anyway, so there are different approaches to tackle that problem that come actually up with a new concept of similarity, a new kind of cluster model, and we try to somehow classify them. So here is an attempt of a taxonomy of those approaches. It is not explicitly the same terminology as in the literature. Most of the literature actually follow this taxonomy, but there are some inconsistencies, so just that you know about that. If you look in the literature, and it's a little bit inconsistent to what we have termed here, don't get confused. So what are the approaches or the classes of approaches? Well, we have a class of so-called subspace clustering algorithms that are restricted to find axis parallel clusters or clusters in axis parallel subspaces. So they do not care about the general task where the relevant subspace can be arbitrarily oriented, but they take care about this scenario where the relevant subspaces can be different ones for different clusters, are axis parallel, which is a very hard assumption because you're rejecting any correlation or neglecting any correlation in the data space. But okay, it's a first approach actually. So those approaches typically find all clusters in all subspaces, and the clusters may overlap. And typically they all follow the same algorithmic subspace search, which is usually a bottom-up approach. And we will have a look in these approaches, of course, later on. Then the second class is the so-called projected clustering approaches. They are still rejected to axis parallel subspaces, but they don't allow overlapping clusters like those here. So each point is assigned to one subspace cluster or to noise, and they typically use a different or the vice versa approach for subspace search. So they typically use a top-down subspace search approach, and we will also have a look on some sample approaches here, of course. And then the third big class here is the solution to the general problem, which is called in our taxonomy correlation clustering, sometimes also arbitrarily oriented subspace clustering, but we will call it correlation clustering. And they explore arbitrarily oriented subspaces. So typically, again, each point is assigned to one subspace cluster, no overlap, and there are completely different subspace search approaches. We will see, or we'll have again a couple of examples here. And then again, there may be some mixed approaches or hybrid approaches that do not perfectly fall into these things here, but we'll try to somehow take this taxonomy because it's more or less exhaustive, not perfectly, but more or less, say 98% exhaustive, to somehow classify the approaches that we want to share with you. So what's coming up? We will talk about subspace clustering approaches. We will talk about projected clustering approaches following our taxonomy. Then we will have a look at so-called pattern-based clustering approaches, which we will find that they are special cases of subspace or projected clustering approaches, and sometimes are even special cases of correlation clustering approaches. And the correlation clustering approaches will be covered at the end, solving the most general problem. So we will start off now with subspace clustering algorithms, once again finding only access parallel subspaces and not the general case. Yeah, so we will start here now.